So again, this means that x is moving to the right. To the right. And then if you have x approaches negative infinity, x goes far to the left. And again, it doesn't matter near the origin. This doesn't describe that at all. It just talks about the ends of the function. Now, one way that we'll write, a couple ways that we'll write this, and we'll look at both of these, is if we just have a sample graph, and this is on your worksheet there, an approximation of this probably. So we have this function here, right? And a couple ways we can describe this. One, kind of the traditional way, is you're going to have y approaches something as x approaches infinity, and then y approaches something as x approaches negative infinity. If you're going to write it this way, you need to have both of these lines. This is what happens as we go to the right. This is what happens as we go to the left. Okay, it'll always be one to the right and one to the left. Okay, now, if I look as we go to the right, I see that there's kind of doing polynomial stuff and bouncing, but I see that here it just goes up to the right forever, right? Well, for up and down, we still use positive infinity and negative infinity, up being positive infinity. So for this one, we would say y approaches infinity as x approaches infinity. So again, that means it goes up as we go to the right. That's all that's saying. It's a mathematical way of saying it goes up as we go to the right. And then down here, it's what happens as x goes to negative infinity. Well, as we go left, it goes down. So we would say negative infinity. So that means down as we go to the left. That's how you write those. Okay. That's sort of the traditional way of writing it. We do want to start incorporating using limits to write this. So this top line could also be written. Now for this, the only additional piece of information, which is a good one, is you have to give the function a name. So we'll just call this one f of x. It says y. We'll call it f of x. So we'll say this was the graph y equals f of x. But you would say the limit as x approaches infinity, now that's LIM for limit. The x approaches infinity is a subscript. It's like the smaller one on a computer of the function f of x. So this is just saying as we go to the right, what does the function do? We still know it goes up, correct? So this is equivalent to this. These mean the same exact thing, just two different forms. This is a little more compact, and I think this tends to confuse people because you put the x's here first, and then you like fill in the thing in front of them, which I think can seem confusing. Where when we use the limit notation, as x approaches negative infinity of f of x, so the limit of f of x as x approaches negative infinity is negative infinity. So these two statements say the same exact thing as those two statements. We need to be able to understand both of them, just like interval notation and inequalities. Like they're sort of interchangeable. You'll see them both. Just different ways of writing. Okay, for our next example here, we have a graph that looks similar to this. If we're going to fill in the blanks here, as we go, as x approaches infinity, which means as we go to the right, it goes down, so that would be negative infinity. And then as x goes to negative infinity, which means as we go to the left, forever, right? We're going way to the left. Doesn't matter at all what happens in here, but we're approaching negative infinity. So those would be your two statements. Now if you wanted to write using limit notation, it would be the limit as x approaches infinity. I guess we'll call it f of x. You need to have a function name in here. Usually you don't see y though, but you see f of x or p of x. Just have something there. It's like if you had a square root symbol with no number under it, it would be weird. If you have a limit with no function after it, it doesn't really mean anything. It's just sort of strange. But this would be negative infinity, and then the limit of f of x as x approaches negative infinity is also negative infinity. Okay, so we've done the front of the worksheet and we've looked at, I don't know, 8 different functions, right? And again, it really just depended on 2 things, is when we look at that polynomial, we only care about the leading term. That's it. So when doing this, be sure it's in standard form before you decide what the leading term is, right? You got to get the highest degree term first. But then once you have that, we care about whether a sub n, the leading coefficient, is positive or negative. And then we care whether the degree is even or odd. That's it. So everything else about the function doesn't really matter in terms of n behavior, just those big pieces there. So there's 4 cases. If n is even, so second power, fourth power, etc., a sub n is positive. So I always think about the graph of x squared here. Does that fit that? Sure. The coefficient's 1, it's an even power. So what do both sides do for x squared? Both go up. So both of these would be infinity. And I went ahead and used limit notation here. So again, I think about this graph right here. Something really nice that, maybe we'll talk about that in a minute, but that was our first case. The second case is n is still even, so I'm still thinking parabola in my head. Like that's an even degree polynomial. But a sub n is less than 0. Well, I know a negative 3x squared opens down, correct? So since I know that this looks like a parabola that opens down, it's going to, both sides will go to negative infinity. Now also notice here, we define the polynomial as being p of x, and within each of these limits I did put p of x, right? Not a huge deal at this point, but as you work more with limits, it could really goof you up. So make sure to kind of identify the particular function you're talking about. So here we have n is odd. I always think about a cubic. You could actually think about a line if you wanted to, but that might kind of weird people out. But I think about like x cubed. A sub n is positive, so I know it looks like this, right? As I go to the right, it goes up. As I go to the left, it goes down. Again, the graph I think of is just like y equals x cubed, right? It has this little kind of thing going on, but it looked like that. Then our last case is when n is odd and a sub n is less than 0. Well, that's going to look like negative 2x cubed or something like that. So it's going to look like that and that. Just flips it, right? So with this one, we get negative infinity and then infinity. So that would be like, I might think about y equals negative 2x cubed. They all behave the same if you get the right even, odd, positive, negative piece. So again, some people might really, if you could just think of the 4 pictures, it might help you to fill in your tables. Some people will just like looking at these and that'll make them really comfortable. What I kind of do is the following. I know that if the degree is even, they're both the same. I know if the degree is odd, they're opposites. Right? Odd, opposite, even, the same. I don't know if that might rhyme. But also if you look, anytime the leading coefficient is positive, like in this case or in this case, as we go to the right, we get positive. So what you'll find is if the leading coefficient is positive, as you go to the right, you'll get positive infinity. If the leading coefficient is negative, as you go to the right, you'll get negative infinity. Right? So the sign of the leading coefficient tells you what happens as you go to the right. If it's positive infinity. If it's negative infinity. I like to pair that with the fact that if it's even, both sides are the same. If it's odd, both sides are different. So I always do the left first, and then I compare if it's even or odd. This is just an idea there on how to do that. So the next thing we want to do is on the paper here is let's look at these 5 functions, and we'll go ahead and see what they are. So just take maybe 5 minutes and try that. Just determine the end behavior without graphing. Like we just want to get a statement for each of these. So number 1 on the worksheet, which of these cases would it be? It was, the leading term was 3x cubed. So what's it look like? What are we going to have? So let's see, n is even, right? Or no, 3x cubed. So that'd be right here. Right, so that you should have these two statements, correct? Like you can't just do one. You got to do one for each end. One for the right, one for the left. Is that good? The second one is negative 1/8 x cubed. So the leading coefficient is negative. And this is a different way you could do it. The leading coefficient's negative, so I know it's down as I go to the right. And then, don't worry, I can do the backwards thing. It's to the right. And then if it's cubed, they're odd, so it's opposite. So it looks like this. Like, and actually, I mean, like, you can do them all, right? You can. There's only 4 positions. It's one of those 4. So which one was it? Negative, an odd. So that'd be this case, right? Was number 2. Number 3 is even, so they're both the same. It's positive, so they're both up. So that would be this case down here. Again, you'd have to write both those statements. 4 is odd and negative. So odd and negative means as we go to the right, it's down, and then this would be up. So that would be this case right here. Okay, and I'm not above putting a little picture on that helps you. You guys just do what helps you, right? If you remember, some people are very formula driven, some people are picture driven, some people are, remember, a little routine driven. Whatever works. Do what works for you. The next one here is x to the 11th is the leading term, so that's positive and odd. So positive, odd, that'd be this one right here. Questions on that? Yeah.
Can you repeat number 1? Or not number 2?
So from last night's homework set, we had this number 41, and we didn't really know a ton about end behaviors yet, or we hadn't really formally gone over it yet. So I wanted to look back at it. I think before we did this, we made a sign table, which wasn't a lot of work, but it was a little bit of work. But still, we see that we have 2 factors here, right? So the factors provide us with x-intercepts. So there's an x-intercept at 1, 0, and this has a multiplicity of 3, right? Because the factor's cubed. So that means it's either going to look like that or that. Kind of, oh, that's not good. Or like that. Right, kind of like a cubic. It's called a point of inflection. It's going to hit, kind of sit there for a minute and go back up. The other one we had was at negative 2, 0. It has a multiplicity of 2. And if the factor is just there once, it doesn't have a multiplicity. We don't even talk about it. It's just when they repeat, when you get a squared or a cubed, we talk about multiplicity. So from here, that means that we're either going to have what looks like a parabola going up or a parabola going down. Now our question before is how do we tell where we start? Well, once we know the end behavior, it's pretty easy to start. But there's a little bit of a catch here. If you get something factored like this, you really never want to unfactor it. You don't want to distribute it because it would be a mess. You may not be able to factor it. Even if you did, you just spent like 15 minutes undoing what you shouldn't have done in the first place. But I don't want to multiply it out because it would take a long time, but I could figure out what it would look like in terms of the leading coefficient really easily. Okay, now, when I do x minus 1 and I cube it, the biggest term is going to be x cubed, correct? And there's going to be a bunch of stuff after it. So kind of the way I think of it is when I start multiplying it out, you're going to get x cubed plus a bunch of stuff, right, in that first parenthesis. The second one, you're going to get x squared plus a bunch of stuff. When you multiply these together, the biggest term is going to be x to the 5th. And then you're going to have a bunch of lower degree terms. So do we know the leading term now? Sure. So this is positive. So a sub n is greater than 0. It's an odd degree. So if I wanted to write the end behavior, I could say the limit as x approaches infinity of f of x, because that's the name of the function. So I said a sub n is greater than 0, so that would be infinity. So that means as we go right, we go up. And then we have the limit as x approaches infinity, or sorry, negative infinity of f of x would give us the opposite, which would be negative infinity. So it's going to look like this. Okay, start low, finish high. Now, with our multiplicity and our end behavior, let's see. There are our two zeros, right? We said we start left low, correct? As we go left, we go down. So it's going to start low. Here, it's going to bounce because it has a multiplicity of 2. So it's going to start low, it's going to bounce. It's going to come back up through this point and do that little multiplicity of 3 thing, but then it'll be above, so it'll finish up high, which is what we wanted. Okay? They need to be in agreement. If you find that you have to cross the x-axis again and there's no x-intercept, something's wrong. Either you missed a multiplicity, or your end behavior is wrong, or something's off. Right? So with this, it starts. Got to be low down here. It's got to be high up here. That's what this tells us. So I'm up here, down here. This was our bounce. Then we do the little thing, and it looks like that. So it's the same graph we had before. Again, notice I didn't put any scale on the y-axis. It's just not, we're not finding values. We're just trying to get the shape. We're trying to show the important things like the end behavior, where there's x-intercepts, where there's bounces, where there's a point of inflection. Those are all things that we'll look at later. The one point, if you do want to put some scale to it, or maybe see what it would look like on a calculator, which is a great way to check your work, it's really easy to find the, even if it's in this form, it's really easy to find the y-intercept. Right? Because remember, the y-intercept is just where x is equal to 0. So if you do that, you get f of 0 is -1 cubed times 2 squared, which is just -4. So you could find that pretty easily if you wanted to, just to give you an idea of what the scale looks like. So that's an example of how we can use our new end behavior along with the kind of bounce stuff to help us kind of construct a good graph there.